Welcome to all of you. This is the second part of this tutorial series about mechanical seal. In the first part of this tutorial series, I discussed about the working principle of mechanical seal and what are the best practices to operate any centrifugal pump to avoid mechanical seal failure. Now, in this part, I will discuss about different type of mechanical seal. Mechanical seal can be divided into different types based on its design or based on its arrangement. For example, mechanical seal can be divided into unbalanced type of seal or balanced type of seal based on its design. It can also be divided into pusher type of seal or non-pusher type of seal, again based on its design. Based on its arrangement, it could be of single seal or multiple seal. Now, again single seal could be of inside mounted or outside mounted. Now, multiple seal can be a pressurized type of seal, pressurized type of dual seal, and even in pressurized type of seal, dual seal can having back to back arrangement or face to face arrangement, or it could be dual unpressurized seal, that is called tandem seal. Now, in this part of video, I will be focusing only on the mechanical seal types based on its design, and in the next part I will discuss about the different type of mechanical seal based on its arrangement. Okay. Now, before I define what exactly is balanced seal or an unbalanced seal, let us first try to figure out the forces acting on the two faces of any mechanical seal. This is rotary part and this is a stationary part, and this is the two seal faces. Now, if you look closely, there are some forces which try to close these two seal faces, okay, and there are some forces which try to open these two seal faces. For example, if you look closely, you will find this a spring is in compressed form. So, it will try to regain its natural position. So, it will exert a force in this direction. So, it will try to close these two forces. Okay. Now, the fluid inside the stuffing box will be having some stuffing box pressure, and it will exert a hydraulic force in this direction, and it will try to close these two seal faces. The liquid film in between the two seal faces will exert a hydraulic force in opposite direction, and it will try to open these two seal faces. So, if I write all these forces numerically, I can write the force by a spring as a closing force, the hydraulic force of a stuffing box as a closing force, and the opening force by the liquid film as a opening force. Now, if this closing force becomes equal to the opening force, then these two different directions forces balance out, and this type of seal design is called balanced seal design. Now, if these two forces, that is closing force, does not equal to opening force, then there will be a net force, and this type of seal design is called unbalanced seal. Okay. Now, if you ask how I can discover whether my seal design is unbalanced or balanced by just visual inspection, for that, if you draw a line from this spring and if you find that line crosses the two seal faces, then that type of seal design is unbalanced seal. Now, if you draw a line and if your line does not cross the two seal faces, then that type of seal design is usually a balanced type of seal design. Now, to go in depth, let us write numerically all those forces which are acting on the two seal faces. Now, this is rotary part, this is a stationary part, and the outer diameter of the two seal faces is D2. The inner diameter of the two seal faces is uh, uh, D3, and the diameter of this shaft is D1. Okay. Now, if you look closely, the stuffing box pressure, the hydraulic force by the stuffing box pressure acts throughout throughout this seal faces up to this shaft. Okay, so for this closing area, you can calculate as pi by 4 this d2 square minus this d1 square, because this closing force also act up to this area. Okay. Now, if you calculate the opening area, then this will act from this point to this point. So, area will be equal to pi by 4 d2 square minus d3 square. So, obviously, closing area is greater than opening area because of this section. Okay. Now, coming to the pressure part, the pressure exerted by the stuffing box because of stuffing box pressure, the hydraulic force, the pressure inside the stuffing box is PS, that is the stuffing box pressure, and the pressure of the liquid film in between the two seal faces uh, the in between the two seal faces could be anything between the stuffing box pressure and the atmospheric pressure, because here the pressure is a stuffing box pressure, here is the atmospheric pressure, and in between these 2 points the pressure will be below stuffing box pressure and above the atmospheric pressure. So, there could be a linear variation, like from this point to this point the pressure will reduce from stuffing box to atmospheric pressure linearly. It can also reduce in different fashion, like concave or convex. For simplicity, let us take an average force, average pressure between these 2 points as a PS stuffing box pressure plus atmospheric pressure divided by 2. That is arithmetic mean. Now, if you since in general stuffing box pressure is much higher than the atmospheric pressure, so we can neglect this atmospheric pressure. So, we have a closing force is equal to a stuffing box into closing area, a stuffing box pressure into closing area, and opening force is equal to a stuffing box pressure divided by 2, that is average pressure, into opening area. So, obviously closing force is greater than opening force because pressure is also high and area is also high. Okay. So, in this case closing force is much higher than the opening force. So, this is an unbalanced type of seal. Now, this type of seal is not recommended when the stuffing box pressure goes beyond 10 kg, because in that case the closing force will be much higher than the opening force, such that there won't be any liquid film between the two seal faces, because this closing force is much higher than this opening force. It will be in direct contact, and there won't be any liquid film between these two seal faces, and the two seal faces will ultimately wear out, and the cell failure will occur. So, to avoid this problem, people invented a different type of arrangement so that these two forces balance out, that is closing forces become opening forces, and for that they put a sleeve on the shaft such that closing area reduces, and closing force become opening force. To write it numerically, this is a sleeve. So, the outer face diameter is again d2, the sleeve diameter is d1, shaft diameter is d3. So, this of course closing area is much lower than the opening area. Closing force is equal to a stuffing box force into closing area, and opening force is equal to a stuffing box for pressure divided by 2 into opening area. Now, we design balance seal, or we design the sleeve diameter such that these two forces become equal. So, if you equate these two forces, you will find that closing area becomes opening area divided by 2. Now, this closing area divided by opening area is defined as balance ratio. Now, if your balance ratio is below 1, then this seal is close to balance seal, and it can sustain a higher stuffing box pressure. Okay. Now, for all this discussion, I did not took spring force. So, a if you account this spring force, then balance ratio becomes slightly it will deviate slightly from 0.5. In general, if balance ratio is greater than 1, then that is an unbalanced seal and that cannot be used for higher stuffing box pressure. And if this balance ratio is below 1, then it is close to balance seal and it can be used for higher pressure application. Okay. Now, balance seal, mechanical seal can also be divided into pusher type of seal or non-pusher type of seal based on its design. Now, to explain these different types, we know that the rotary part of mechanical seal is usually made of softer material like carbon, and the stationary part of mechanical seal usually made of harder material. So, what happens during operation, this softer material carbon wears out and it creates a gap between the two seal faces. Now, to compensate this gap, the rotary part must move such that to maintain it maintains the face closure between the two seal faces. Now, if this compensation took place by the pushing force of hydraulic force by stuffing box and a spring force, such that this O-ring moved in this direction to compensate this gap, then this type of seal is called pusher seal, because uh, because the pushing force by the hydraulic force and spring force, this O-ring moves and finally this face closure maintained. Okay. Now, because of this movement, in all pusher type of seal, this O-ring is in dynamic condition, and also because of this dynamic condition, when this O-ring moves, it creates a wear on this shaft, and this wear area is called fret. So, pusher type of seal having inherent problem that it creates a fret on the shaft. Also, when this carbon faces wear out, that solid carbon build up ahead of O-ring. Also, at that time, some stuffing box liquid will come out between the two seal faces, and it condenses and forms solid ahead of this O-ring. So, what happens ultimately, this blocks the movement of this O-ring, and so when further faces wear out, then this face closure cannot occur, and ultimately seal will fail prematurely. Seal will hang out because of this solid buildup, and seal will fail prematurely. Now, to avoid these two problems, that is fretting problem and the seal hangout, there is a different type of seal design called non-pusher type of seal. There is a fixed or a static O-ring, that is secondary seal is in a static condition. There won't be any pushing force and the movement of O-ring to compensate the gap caused by the carbon face wear. To compensate the gap between the carbon face wear, in non-pusher type of seal, there is a different seal component called velo. It could be, of course, metallic or elastomeric, whatever it may be. When this the face wear occur, this elastomers or metallic bellow expand and maintain the face closure. So, this this avoid the soft fretting or soft wear, and also when this solid buildup occur because of this carbon face material and the stuffing box liquid condensation, this does not create any hang up. So, ultimately non-pusher seal does not have these two problems which arises due to pusher type of seal design. Okay. Now, I again use different type of different links to create these slides, mainly from I used images from FlowSolve websites and also used different links. I would like to give credit to all those links and images, and in the next part of my video I will discuss about the different type of seal based on its arrangement. Thank you.